Mars could kill astronauts long after the landing is called a success. That is the part most people miss. The real danger is not the terrifying descent through a thin alien atmosphere. It is not the freezing nights. It is not the global dust storms that can swallow the planet for weeks. And it is not even radiation alone. The true threat is something far more dangerous. It is survival. Because getting humans to Mars may be one of America's greatest engineering victories. Keeping them alive there is a completely different battle. For decades, Mars has been sold as the next giant leap, a red frontier, a backup planet, the next chapter of human civilization. Powerful rockets dominate headlines. Massive boosters rise from launch pads. Private companies promise colonies. Government agencies talk about deep space leadership. The message feels clear. America is getting ready for Mars. But beneath the excitement is a darker reality. A Mars mission could land perfectly. The crew could walk on the surface, flags could wave, history could be made, and the mission could still slowly become a catastrophe. Not in the first hour, not in the first week, but months later, or years later, because Mars is not simply a place to visit. Mars is a system designed to break the human body, the human mind, and every machine keeping them alive. This is where the conversation often becomes dangerously shallow. Most people think the biggest challenge is building a rocket powerful enough to travel millions of miles. That challenge is enormous, but it is also only the beginning. The harder question comes after arrival. How do humans survive on a world where nearly everything wants them dead? Mars has almost no breathable oxygen. Its atmosphere is over 95% carbon dioxide. Its air pressure is so low that exposed bodily fluids could boil. Its soil contains toxic chemicals called perchlorates. Its average temperature is around minus 80 degrees Fahrenheit. Its dust may damage lungs, machines, electronics, and habitats. And unlike Earth, Mars has no global magnetic shield to properly defend life from deep space radiation. That means danger does not stop after touchdown. In many ways, it begins there. This is why physicist Brian Greene's broader perspective matters. Greene often speaks about humanity's ambition with both awe and caution. Science can push boundaries, but nature does not care about optimism. The laws of physics do not reward confidence. Mars is not conquered by excitement. It is conquered by solving thousands of deadly biological and engineering problems at once. That distinction changes everything. Because right now, the United States may be developing extraordinary transportation systems. NASA Artemis era is pushing human space flight forward. SpaceX is building vehicles more powerful than anything in modern history. The dream feels closer than ever, but there is a hidden gap between reaching Mars and living on Mars, a massive one. Sending astronauts there for a short mission is one challenge. Creating a stable survival system for years is another. And that second challenge may be far beyond what current systems can guarantee. This is the part that often gets buried under national pride. Mars is not the moon. Apollo astronauts traveled about 240,000 miles. Mars can be over 140 million miles away. A rescue mission is not realistic. Emergency return is not simple. Supply chains are fragile. Communication delays can stretch to 20 minutes one way. That means astronauts may face lethal problems alone. No immediate help. No quick decisions from Earth. No instant correction. For the first time in human history, People could become so distant that survival depends almost entirely on self-sustaining systems functioning perfectly on a hostile planet. And perfection is rare, even on Earth. The International Space Station is often seen as proof humans can live in space. But there is something most people forget. Astronauts on the ISS are only hours away from Earth in The ISS also depends heavily on constant resupply, maintenance, and communication. Mars settlers may not have that luxury. This is where the illusion begins to crack, because Mars is not merely a long-distance space station. It may become the harshest survival experiment humans have ever attempted. Every calorie matters. Every drop of water matters. Every oxygen molecule matters. Every seal, circuit, crop system, and psychological response matters. One small failure in a closed environment can trigger disaster. A damaged habitat, a contaminated food supply, a life support breakdown, a medical emergency, a mental collapse. On Earth, these are crises. On Mars, they can become extinction events for an entire crew. Yet public discussions often stay focused on launch dates. Who gets there first? Which nation leads? Which company dominates? This creates a dangerous misunderstanding. Mars is not a prestige project. It is not simply a race. It is survival science at its absolute limit. And this is where America's readiness becomes a serious question. Is the United States building systems for true interplanetary survival? Or are we still mainly building transportation for historic arrival? Because those are not the same thing. A rocket can carry humans to Mars. But rockets alone do not solve radiation exposure over years. They do not solve long-term muscle deterioration in reduced gravity. They do not solve sustainable agriculture in toxic soil. They do not solve psychological endurance under extreme isolation. They do not solve childbirth, aging, surgery, or civilization on another world. This is why some experts quietly worry that the first successful Mars landing could create false confidence. A planted flag could make humanity feel victorious. But surviving decade after decade is the real mission. And history has shown that exploration often underestimates hostile environments. On Earth, early explorers faced oceans, deserts, polar ice, and disease. Mars combines extreme versions of all of them, with one terrifying difference. There is no natural biosphere to fall back on, no breathable air, no ecosystems, no rescue ships over the horizon, only systems. And if those systems fail, Mars does not forgive mistakes. That reality shifts the entire conversation. This video is not about whether America can reach Mars. It is about whether America is truly prepared for what happens after. The hidden biological threats, the engineering weaknesses, the infrastructure gap, the survival myths, the brutal truths that flashy rocket launches rarely reveal. Because the future of Mars may not be decided by launch power. It may be decided by whether human beings can build a completely artificial version of Earth strong enough to survive millions of miles from home. That is a far more difficult challenge, and one that most people seriously underestimate. By the end of this video, you will understand why Mars may be humanity's boldest dream and most dangerous illusion at the same time. You will see the overlooked scientific barriers, the hidden survival crisis, and why reaching the red planet could be the easy part. The real question is whether America is prepared to keep people alive once they get there. Welcome to the channel. Subscribe now because this journey into the future of human survival is only getting started. The first deadly truth about Mars begins before astronauts even land. Distance, not danger from aliens, not mechanical explosions, distance itself. Mars is not the moon. That difference changes everything. When Apollo astronauts traveled to the moon, they were about 3 days from Earth. 3 days. If disaster struck, there was at least a path home. NASA engineers could respond quickly. Communication was nearly instant. The moon was distant but still connected. Mars breaks that connection completely. With current propulsion systems, a one-way trip to Mars usually takes around 6 to 9 months. That is half a year or more trapped inside a spacecraft, not exploring, not landing, just traveling inside a confined metal habitat, far from Earth, far from rescue, far from any real chance of immediate survival support. And that timeline only works during favorable planetary alignment. Earth and Mars orbit the sun at different speeds. That means launch windows are limited. Miss one, and astronauts may wait many months for another opportunity. This creates a terrifying possibility. A crew could reach Mars successfully and still be stranded there far longer than planned. This is one of the least discussed dangers. Mars is not simply far away. It is logistically unforgiving. During the mission, astronauts would move millions of miles from Earth's protective systems. The farther they travel, the more impossible rescue becomes. A serious medical emergency midway to Mars is not like an ISS evacuation. There are no emergency return capsules, no nearby station, no rapid response. If someone develops appendicitis, suffers a stroke, or experiences equipment failure, the crew may have no outside solution. They become their own doctors, their own engineers, their own survival system. For the first time in history, humans may enter a zone where help from Earth is mostly advice, not action. And even that advice arrives late, because communication delay is brutal. Depending on planetary position, signals between Earth and Mars can take between 4 and 20 minutes one way. That means a simple message can take 40 minutes for a question and response. A fire in a habitat, a failing oxygen system, a navigation issue, a psychological breakdown. Mission control cannot instantly step in. There is no real-time guidance, no immediate troubleshooting, no voice saying, "Press this now." Astronauts must solve life or death problems largely alone. This delay may sound technical. It is not. It is psychological warfare. For decades, astronauts have relied on constant communication with Earth. A Mars crew could experience long periods where silence itself becomes a stressor. And silence in deep space is not peaceful. It can become oppressive. The vast emptiness outside the spacecraft may create a level of isolation no human society has ever truly tested. Even Antarctic stations and submarines still exist on Earth. Mars crews would watch Earth shrink into a distant star-like object. Family becomes unreachable in any meaningful emotional sense. Normal conversation disappears. Every message becomes delayed. Every crisis becomes internal. Some researchers believe this prolonged isolation could trigger depression, cognitive decline, social tension, or dangerous decision-making. Small interpersonal conflicts could become mission-threatening. A broken water recycler is dangerous. A broken team dynamic may be worse. Apollo 13 became famous because NASA could mobilize instantly to save lives. Mars offers no Apollo 13 miracle. There may be no rapid improvisation from Houston, no quick return, no splashdown in the Pacific. Mars astronauts may cross a point where going forward is safer than turning back. That changes the psychology of exploration forever. For the first time, humanity may send people so far away that survival depends not on bravery alone, but on whether every fragile system keeps working in the cold silence of deep space. Space does not need fire to kill you. Sometimes it uses particles, invisible, silent, relentless. One of the most terrifying dangers on a Mars mission cannot be seen, smelled, or physically felt in the moment. Radiation. Not the kind from a hospital scan. Not the brief exposure from airport security. Deep space radiation is something far more brutal. Beyond Earth's magnetic shield, astronauts enter a cosmic firing range. High-energy particles from distant supernovas, exploding stars, and violent solar eruptions race through space at nearly unimaginable speeds. These are galactic cosmic rays, and they can pass through human tissue like microscopic bullets. Earth protects life from much of this chaos. Our planet's magnetic field deflects many charged particles. Our thick atmosphere absorbs others. It is one of the hidden reasons life thrives here. Without those defenses, humanity's biological fragility becomes brutally clear. A spacecraft traveling to Mars leaves much of that protection behind. This means astronauts may spend months bathing in radiation levels far beyond normal Earth conditions. NASA has studied this problem for years. Data from the Curiosity rover's radiation assessment detector revealed that a round-trip Mars mission could expose astronauts to radiation doses approaching or exceeding current career safety thresholds. And that estimate does not even include every worst-case solar event. A major solar particle storm during transit could become catastrophic. This is where the danger becomes deeply unsettling. Radiation does not usually kill instantly. It damages slowly. DNA strands break. Cells mutate. Cancer risk rises. But lesser-known threats may be even more disturbing. Recent research suggests prolonged cosmic radiation exposure may damage the brain itself. Animal studies have shown possible cognitive impairment, memory loss, reduced decision-making ability, and neurological changes after exposure to charged particles similar to those in deep space. That means astronauts on a Mars mission may not just face physical deterioration. Their judgment could also be affected. On a mission where every decision matters, that possibility is chilling. A tiny navigation mistake, a delayed repair, a poor systems choice. Radiation may quietly weaken the very minds needed to survive.
And Mars itself offers only limited relief.
Many people assume landing solves the radiation problem. It does not. Mars has a thin atmosphere, but it is less than 1% as dense as Earth's. Its global magnetic field is essentially gone. Billions of years ago, Mars likely lost much of its protective magnetosphere. That loss helped transform it from a wetter world into the hostile desert seen today. Now, the surface remains vulnerable. Radiation levels on Mars are lower than deep space, but still significantly higher than Earth. This means astronauts may leave one dangerous radiation zone only to enter another. Habitat design becomes critical. Some scientists propose burying living quarters beneath Martian soil or ice for shielding. Others discuss water walls or hydrogen-rich materials. But each solution creates new engineering problems. Weight is one of the greatest enemies of space travel. The heavier the shielding, the more fuel required. The more fuel required, the more expensive and difficult the mission becomes. This creates a deadly compromise. Protect astronauts better, and missions become harder to launch. reduce mass, and crews face greater biological risk. No perfect answer exists yet. Even spacesuits become a concern. Routine surface exploration could expose astronauts repeatedly. Every excursion adds cumulative danger. And unlike many threats, radiation damage often compounds over time. You may survive exposure today, only to face consequences years later. Cancer, organ damage, neurological decline, potential fertility issues. This is why some experts argue radiation is not just another challenge. It may be the biological wall separating exploration from settlement. Because rockets may carry humans to Mars, but unless science finds stronger protection, the journey itself could slowly alter their bodies and minds long before the red planet ever becomes a true home. The human body was built for Earth. Every heartbeat, every bone, every muscle fiber, every biological system evolved under one constant force: Earth's gravity. Remove that force, and the body begins to change. Not always immediately, but steadily, and sometimes dangerously. Before astronauts even reach Mars, their bodies may already be deteriorating. During the 6 to 9 month journey, crews would spend most of their time in microgravity. Weightlessness may look graceful from Earth, floating, spinning, moving effortlessly. But inside the body, it triggers a silent breakdown. Muscles begin to weaken because they no longer work against normal resistance. Legs and backs are hit especially hard. Bone density also drops. Without gravity stressing the skeleton, bones can lose minerals faster, similar to accelerated osteoporosis. Some astronauts on long missions have experienced measurable bone loss each month. That means a Mars crew could arrive weaker than when they left. And weaker on Mars may still not be enough, because Mars has gravity, just not much. At roughly 38% of Earth's gravity, Mars pulls on the body more than space, but far less than home. This creates a strange biological unknown. Scientists understand microgravity damage reasonably well. They understand Earth's gravity well, but long-term human life in partial gravity remains largely untested. No human has ever lived for years in Martian gravity. That means one of the biggest survival questions remains unanswered. Is 38% enough to maintain healthy bones, muscles, heart function, and reproduction over decades? No one truly knows. And uncertainty on Mars is dangerous. The cardiovascular system may also suffer. In microgravity, bodily fluids shift upward. Faces puff. Vision can change. Some astronauts experience pressure changes that may affect eyesight long term. The heart itself may weaken because it works less hard to pump blood against gravity. Returning to stronger gravity after months in space can trigger dizziness, fainting, and reduce physical performance. Now place that weakened body on a cold, hostile planet where every movement matters. Simple tasks could become exhausting. Emergency repairs could become physically brutal. And then there is the immune system. Spaceflight appears capable of altering immune responses. Some dormant viruses in astronauts have reactivated during missions. Stress hormones rise, sleep disruption increases, isolation compounds biological strain. A small infection on Earth may be manageable. On Mars, it could become a crisis. This becomes even more alarming when considering medical care. There are no emergency rooms on Mars, no surgical centers, no trauma specialists. A burst appendix, a kidney stone, a dental abscess, a fracture, These ordinary human problems could become life-threatening when treatment options are limited and evacuation is impossible. Even medications may degrade over time due to radiation exposure. Some studies suggest pharmaceuticals could lose potency during extended missions. That means astronauts may carry medicine that slowly becomes less reliable millions of miles from Earth. Then comes one of the least discussed questions of all: human reproduction. Scientists still do not fully understand how conception, fetal development, or childhood growth would function in Martian gravity and radiation conditions. This is not a small issue. A long-term civilization requires more than survival. It requires biological continuity. Mars may challenge that at the deepest level. And survival is not just physical. Psychological strain may be equally severe. Humans evolve with open skies, natural ecosystems, weather, social diversity, and sensory variation. Mars offers confinement, artificial habitats, recycled air, routine, isolation, distance. For years, the brain may begin to suffer under monotony, confinement, and prolonged stress, depression, conflict, cognitive fatigue, emotional instability. These are not side concerns. They may become direct survival threats. Because on Mars, the body is not simply exploring another planet. It may be fighting every day against conditions it was never truly designed to endure. Mars looks empty, but that emptiness can be deceptive. For years, the dream of colonizing Mars has been powered by one powerful idea: humans will live off the land, use Martian soil, extract water, make oxygen, grow food, build fuel, create a second home for civilization. It sounds bold, efficient, almost inevitable, but the reality is far harsher. Because Mars is not Earth waiting to be developed. It is a hostile planet where nearly every resource comes with hidden danger. Take the soil. At first glance, Martian regolith seems useful. It covers the planet. It could help build habitats, shield against radiation, maybe even support agriculture. But there is a major problem. Martian soil is not normal dirt. Data from landers and rovers revealed that it contains perchlorates. These are toxic chemical compounds that can interfere with thyroid function and harm human health. In high enough concentrations, perchlorates may damage blood production and create serious long-term biological risks. Even worse, Martian dust is extremely fine. It clings, it spreads. Some scientists compare its behavior to hazardous industrial dust. That means astronauts may track toxic particles into habitats, equipment, or even lungs. Growing crops in untreated regolith may not simply fail. It could poison systems. Then comes water. Mars once had rivers, lakes, perhaps even oceans. Today, much of its accessible water exists as ice, buried deposits, or chemically bound molecules. This has created optimism. If there is water, there is life support. But finding water is not the same as building a reliable civilization around it. Extraction on a meaningful scale remains largely theoretical. Mining ice from frozen underground reserves would require energy, heavy machinery, purification systems, and maintenance under brutal conditions. Dust storms, equipment wear, freezing temperatures, and system failure all complicate this process. A few leaders are one thing. Supporting dozens or hundreds of people continuously is another. Then there is oxygen. NASA MOXIE experiment on the Perseverance rover made headlines by successfully producing oxygen from Mars' carbon dioxide atmosphere. It was a breakthrough, but there is an overlooked detail. MOXIE is roughly toaster-sized. Its oxygen output is tiny compared to what a human settlement would require. A colony would need industrial-scale oxygen generation operating constantly with backups, repairs, and power stability. One small experiment proving concept is not the same as planetary infrastructure. And infrastructure may be the true dividing line between exploration and survival. A Mars outpost needs more than air and water. It needs fuel production, food systems, waste recycling, medical manufacturing, construction materials, electronics repair, replacement parts. On Earth, civilization depends on massive supply chains and industrial networks so vast most people never think about them. Mars would begin with almost none of that. A broken valve or damaged circuit could become catastrophic if no replacement exists. Shipping every spare part from Earth is not realistic long term. Launch costs, delays, and planetary distance make dependence dangerous. This is why true colonization requires closed-loop ecosystems. Systems where water is recycled, oxygen regenerated, waste repurposed, and food sustainably grown. Essentially, humans would need to build an artificial Earth inside machines.
Completely.
And closed-loop life support remains one of the hardest engineering challenges ever attempted. Even small imbalances can spiral. Too much carbon dioxide, crop disease, water contamination, mechanical failure. A colony may not collapse from one dramatic event. It may fail from small interconnected weaknesses. This is the deeper reality. Current Mars plans often focus on landing humans. That alone would be historic. But landing is not settlement. A flag is not civilization. A base is not self-sufficiency. Right now, humanity is far closer to visiting Mars than truly living there. Because surviving on another planet means recreating the systems of Earth on a world that offers almost none of them naturally. America knows how to build powerful machines. That part is clear. The United States has pushed aviation, nuclear technology, computing, and spaceflight farther than most nations in history. And now, the race toward Mars is accelerating again. Massive rockets are growing larger. Private aerospace companies are testing reusable systems at extraordinary speed. NASA is developing deep space strategies. Political speeches frame Mars as the next great frontier. From the outside, it can feel like humanity is on the edge of becoming interplanetary. But there is a dangerous illusion hidden inside that momentum. Building the vehicle is not the same as building survival. This may be one of the greatest gaps in the modern Mars dream. Launch systems are improving faster than life systems. In simple terms, America may be getting better at sending humans to Mars than keeping them alive after arrival. That distinction could decide whether Mars becomes a triumph or a tragedy. History has always celebrated firsts. First flight, first orbit, first moon landing. Being first carries prestige, power, national pride. It shapes headlines and political legacy, and Mars may trigger that same mindset. Who lands first? Who plants the flag? Who makes history? But Mars punishes symbolic victories, because planting a flag is a moment. Building civilization is a system, and systems are far harder. A true Mars settlement needs infrastructure on a scale most people rarely consider. Not just habitats, power grids, reliable energy, backup energy, water purification, food production, medical systems, waste recycling, industrial repair, material processing, communication networks, governance structures, psychological support, security protocols. population sustainability. This is not just a mission. It is the construction of an entirely new branch of civilization from near zero. Even on Earth, advanced cities depend on enormous hidden infrastructure. Electricity networks span continents. Agriculture relies on global trade. Factories depend on mining, logistics, and specialization. Hospitals need pharmaceuticals, supply chains, trained personnel, and emergency response. Mars begins without those foundations. That means every essential system must either be brought, built, or invented under extreme conditions. And every missing layer creates vulnerability. This is where policy often becomes short-sighted. Political systems naturally reward visible achievements. A successful landing is easier to celebrate than decades of slow infrastructure development. A rocket launch creates headlines. A functioning sewage system on Mars does not. But civilization depends more on the second than the first. This creates a strategic imbalance. Funding may prioritize transportation milestones over long-term resilience. Short missions are easier to justify than generational settlement systems. The result could be a nation capable of reaching Mars while still lacking the mature survival architecture needed to stay. This is not failure of ambition. It is the danger of incomplete ambition. Even governance becomes a hidden challenge. Who makes decisions on Mars during crisis? NASA? Private corporations? International coalitions? Autonomous crews? Legal systems on Earth may not fully apply millions of miles away. Resource disputes, command structures, psychological strain, and ethical questions may become critical faster than expected. Mars is not just an engineering problem. It may become a political and civilizational one. And then there is redundancy. On Earth, backup systems are everywhere. If one hospital fails, another may help. If one power station goes offline, larger grids compensate. Mars may not offer that luxury. One reactor failure, one agricultural collapse, one manufacturing disruption. Without deep redundancy, isolated systems can cascade. This is why survival may depend less on breakthrough rockets and more on invisible reliability. The United States could absolutely become the first nation to place humans on Mars. But first arrival and long-term endurance are not the same achievement. One proves transportation, the other proves civilization. And Mars may ultimately judge humanity not by who arrives first, but by who can transform a fragile outpost into a self-sustaining world before ambition outruns survival. There is a deeper way to look at Mars that goes beyond rockets and timelines. It is a question of scale, not political scale, not engineering scale, cosmic scale. Physicist Brian Greene often speaks about this gap between human ambition and the size of the universe. Humanity builds fast, thinks fast, dreams fast, but the universe operates on laws that do not bend to urgency or optimism. Mars does not care about human timelines. It does not care about national competition. It does not respond to enthusiasm. It responds only to physics, chemistry, and biology. That is where the tension begins. Mars represents one of the most exciting scientific frontiers in human history. A nearby world, a world that once had rivers, possibly lakes, maybe even conditions that could have supported life long ago. But today it is a reminder that planets do not stay friendly forever, and reaching it does not guarantee survival on it. This is where optimism often runs ahead of reality. Technological progress can feel unstoppable. Every year brings faster rockets, better materials, smarter systems, more powerful computers. But biological systems do not evolve at the same speed. Human lungs, bones, immune systems, and psychology are still designed for Earth, not Mars, not deep space, not radiation exposure for years at a time. This creates a hidden imbalance. Engineering can outpace biology. Machines can improve faster than humans can adapt. And that gap may be one of the most important challenges in space exploration. Brian Greene often highlights something subtle but powerful. Science is not just about possibility. It is about limits. Every law of physics draws a boundary. Every biological constraint sets a condition. And every successful mission must operate inside those limits. Mars pushes against many of them at once. Radiation limits, energy limits, material limits, psychological limits, ecological limits, even information limits. Because communication delays reshape decision-making itself. The deeper lesson is not just how to reach Mars. It is how to survive within its constraints without breaking human life in the process. There is a temptation to believe that more technology automatically solves these problems. Stronger shields, faster engines, bigger habitats, smarter AI systems. But survival on Mars may not be solved by scale alone. It may require entirely new breakthroughs. Closed ecosystems that function for decades without failure. Radiation protection that does not depend on massive weight. Self-repairing infrastructure. Artificial biology that supports human life beyond Earth conditions. These are not small upgrades. They are foundational shifts. And some of them do not yet exist. This is where the Mars mission becomes more philosophical than technical. It stops being about conquest. It starts becoming about adaptation. Can human life be extended beyond Earth in a stable and sustainable way? Or is Earth the only environment where complex human civilization can truly thrive long term? Mars becomes a test of that question, not just for engineers, not just for astronauts, but for science itself, because every system sent to Mars must survive without Earth as a safety net. That changes the meaning of success. A mission can no longer rely on backup plans from home. It must function as a complete, isolated world. That is a level of independence humanity has never achieved before. Brian Greene's perspective helps sharpen this reality. The universe is not hostile in a personal sense. It is indifferent. And indifference can be more dangerous than hostility.
Because it does not warn. It does not negotiate.
It simply follows rules. And those rules decide survival. Mars may still represent the future of humanity, but only if the gap between ambition and readiness is closed. Only if survival systems become as advanced as launch systems. Only if biology, ecology, and engineering evolve together instead of separately. Otherwise, Mars may remain a symbol of progress that arrives before the foundation is strong enough to support it. Mars is closer than it has ever been in human history. The rockets are real. The missions are planned. The technology is advancing faster every year. On paper, reaching Mars no longer feels like science fiction. It feels like an engineering problem waiting to be solved. But there is a deeper truth hidden behind all of this progress. Reaching Mars is not the same as surviving Mars. Landing is only the first step, a brief moment of success, a flag in red dust, a headline written across Earth. After that moment, everything becomes harder, because Mars does not reward arrival. It challenges continuation. The real race is not about who gets there first. It is about who can stay alive after the engines stop working, who can maintain air, who can maintain water, who can maintain food, who can maintain sanity. Survival on Mars is not a single breakthrough. It is thousands of systems working together without failure for years. Radiation must be controlled. Human biology must be protected. Infrastructure must be built from almost nothing. And every system must function without Earth stepping in to fix it. That is where the true difficulty begins. Without solving these problems, Mars missions risk becoming something very different from victory. They could become isolated tragedies far from home, not because humans lack intelligence, but because survival on another world demands more than intelligence alone. It demands a complete transformation of how life is supported, how systems are designed, how failure is prevented, and how independence is achieved in an environment that offers no forgiveness. The biggest challenge is not space travel itself. It is whether humanity can stop being completely Earth-dependent, whether human life can be rebuilt in a way that works beyond a single planet. That is the real boundary being tested. Not just engineering limits, but biological limits, ecological limits, and civilizational limits. Mars becomes more than a destination in this view. It becomes a mirror, a reflection of how fragile life really is when removed from its original home, and a test of whether that fragility can ever be strengthened enough to survive elsewhere. The question is no longer just about reaching the red planet. It is about whether human beings can truly become an interplanetary species without breaking in the process. Mars may not simply be the next step in exploration. It may be the ultimate test of human survival itself. If you enjoyed this deep dive, like the video and subscribe to the channel. More science and space stories are coming that reveal what lies behind the future humanity is racing toward.